of 30 degrees. Now, how am I doing that, you might ask? Well, remember, the cosine is the adjacent divided by the hypotenuse. And if I multiply the hypotenuse, which is the magnitude 5, times the cosine, then all I'm left with is the x component. It's just a simple cancellation. Right? So if I take the hypotenuse times the adjacent over the hypotenuse, this cancels and I'm left with just that.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, welcome back. This is lecture number 9. This will be a basic trigonometry review. Now, we don't need a lot of trigonometry for the kind of physics problems we'll be solving in this course. But to start with, let's just remind ourselves about some of the special properties of right triangles. And the first thing that should come to mind is that if I have a right triangle, denoted by this right here, then the Pythagorean theorem holds, which says that c squared is equal to a squared plus b squared. Right, so actually let me write that out graphically. What does that mean? That means that if I have a square side length A, and I have another square side length B, this is the tough one to draw, then the sum of the area of those squares is equal to the area of the square on the longest side, which is always directly across from the right angle. So this is Pythagorean's theorem. A squared plus b squared equals c squared. And maybe we'll just do a little example on this one. So let's let a be equal to 3, so b be equal to 4, and we'll let c be equal to 5. So let's just confirm that this is really a right triangle. We'd have 3 squared plus 4 squared equals 5 squared. Well, 3 squared is 9, 4 squared is 16, 5 squared is 25, and we see that 9 plus 16 is indeed equal to 25. So these side lengths are valid for a right triangle. That I would really call maybe geometry. So we haven't done the trigonometry yet. So what do we need from trigonometry? Basically, we consider a right triangle. This time I'm going to label the sides a little bit differently. I'm going to call this longest side across from the 90-degree angle the hypotenuse. I'll just label it as h. I'm going to call this side, well, first I'm going to label this angle and call it angle theta. So I'm going to define the basic trigonometric functions in terms of this angle theta on this right triangle. We call the side opposite from the angle of interest the opposite side, OPP. And we call the side that is adjacent to that angle ADJ. Now, for a given triangle, like say the 3, 4, 5 triangle, the ratio of the opposite side to the adjacent side will be the same for similar triangles. So if I were to extend this out just a bit, that's a terrible line there, so I can fix that. Like so. If this was originally 3, then this new side length would be 6. If this was originally 4, then this new side length would be 8. And so we'd have a ratio of 8 over 6, which is the same as 4 over 3. This we can write as 4 times 2, and this we can write as 3 times 2. The 2 and the 3, the two 2's cancel in the numerator and the denominator, and this is the same ratio. So this is the essence of these trigonometric relationships. Then we can define some special functions. The sine of theta we'll define as the ratio of the opposite side over the hypotenuse. Opposite over the hypotenuse. The cosine of theta we'll define as the adjacent over the hypotenuse. And finally, the tangent of theta is defined as the opposite over the adjacent. this is also equal to, and you can show this algebraically, the sine of theta divided by the cosine of theta. These are the basic, really the two that we'll need the most are these guys right here, the sine and the cosine. Why do we need them? Because we want to specify stuff in terms of the angle. And we'll see that when we start talking about vectors in the next lecture, that we'll want to specify things in terms of, say, an incline. Say we're launching a cannonball. Instead of firing it straight ahead, we're going to fire it 30 degrees up into the air. That 30-degree angle we'll use to break down the velocity vector into its x and y components. So it's going a little bit in the x direction, it's going a little bit in the y direction. And so we'll use these trigonometric functions to do that for us. The evaluation of these, you can look up in a table, or you can use a scientific calculator to find the values for it. So if I were to type in, say, the sine of 45 degrees, my calculator would spit out for me the decimal equivalent of the square root of 2 over 2, for example. That said, there are a few basic angles that you'll want to remember, and I'm going to write them down right here. So if this is the angle theta, and I'm going to work in degrees. I know that people will talk about working in radians, and I'm not even going to really, well, I guess I could define quickly what radians are. If we imagine that a unit circle has 360 degrees into it, then we can think that the circumference of a circle, you might recall, is equal to 2 pi times the radius. Well, if we let the radius be equal to 1, so we're talking about a unit circle, then the distance around that circle is 2 pi. That's the length. That's the circumference. So to equate 2 pi with 360 degrees gives you the relationship between radians and degrees. But I like to work in degrees because we think in degrees, not in radians. So let me just write the sine of theta, and also I'm going to give you the cosine of theta. If you need the tangent of theta, you can again take the ratio of the sine to the cosine, but I don't think we're going to have a lot of use for the tangent of theta in this course. So the first angle to consider is 0 degrees. Well, just imagine that this triangle had a 0-degree angle. Well, what would the length of the opposite side be? Right? Watch it as it walks down like this. The opposite side gets smaller and smaller and smaller, and it becomes 0. So the sine of theta, being the opposite over the hypotenuse, would be 0. The cosine, on the other hand, as the hypotenuse moves closer and closer to the adjacent line, these two become one and the same. And so the ratio of the two is just 1. So the cosine of 0 degrees is 1. The next angle to consider is 30 degrees, 45 degrees, 60 degrees, and then 90 degrees. And so I'm going to jump all the way to 90 degrees. That would be where the hypotenuse is angled up all the way to make a 90-degree angle, and you can see that the adjacent is now the side length that becomes 0. So it's the cosine of theta, which is 0 at 90 degrees. The sine of theta, on the other hand, the hypotenuse and the opposite side are of the same length, and so the ratio of those two is just 1. And so the sine of 90 degrees is just 1. Now, with that said, I'm not going to show derive specifically these three special angles in the middle, but I will give you a mnemonic to remember them because we'll use them all the time. And the mnemonic is 1, 2, 3. And it's 1, 2, 3, all over 2. So these three values in the middle, 35 degrees, which is 15 away from 30, and 15 away from 60. Right? So these are equal distance in the two different directions, increasing or decreasing the angle. And maybe if I wrote this a little bit neater, a little more space between it. So 1, 2, 3. You can always, and there's always a square root in the numerator, but the square root of 1 is just 1, so I'll eliminate that here. Now for the cosine of theta, it's exactly the opposite. It's 3, 2, 1. So square root of 3 over 2, square root of 2 over 2, and then 1 over 2. So you see there's this relationship between them. At 45 degrees, the sine and the cosine are equal, which makes sense since 45 degrees kind of bisects 90 degrees, and so you get an equal adjacent component and opposite component. There's just as much rise as there is run, if you want to think of it that way. So these are the basic angles that we use in the problems that we work. If we had occasion to do something that was a little bit strange, like say we calculate the sine of 37 degrees, then you can use your graphing calculators to do that. I think that's pretty much all I wanted to say. Maybe just bring the bring it back around to the Pythagorean theorem once again. So notice that we have that the opposite is the, if I write the Pythagorean theorem in terms of h, opposite, and adjacent, it looks like this. H squared equals opposite squared plus adjacent squared. And if I divide both sides of this by h squared, then h squared over h squared is 1. The opposite squared over hypotenuse squared, this is the same thing as opposite over hypotenuse quantity squared. And the same thing for the adjacent over the hypotenuse squared. But opposite over hypotenuse, that's just the sine of theta. Of course, this is squared. The way we write that is like this. We put the squared sign right there. And the adjacent of the hypotenuse, well, that's just the cosine. So I get the cosine squared of theta right here. And this is the equivalent of the Pythagorean theorem in terms of the trigonometric functions, that the sine squared of theta plus the cosine squared of theta is equal to 1. So we've kind of come full circle, so to speak. And I think that's all we need to say about the basic trigonometric functions. We may use trig identity here or there. I think we will. For the range equation, you can look these up in books. You probably studied it if you took trigonometry or pre-calculus. But other than that, we're going to have a great deal of we're going to have a lot of usage of the trig functions, but we will use the sine and the cosine pretty regularly, mostly in doing 2D kinematics. This is lecture 10 on vectors. So first off, what is a vector and how do we distinguish it from a scalar? Scalar is a quantity that just has a magnitude. The temperature in the room, for example, is a scalar quantity. A vector, on the other hand, has a magnitude and a direction. So, for example, if I'm driving my car at 55 miles per hour on the interstate and I'm headed due north, I could say that my velocity vector is 55 miles per hour north. So you have to specify a direction. Vectors, if we can graph them on an XY graph like this, they'll mean something different than what you think originally. So if I call this my origin, I could create a vector which has some magnitude. This would be a displacement vector, by the way. We could call it R. And I will specify it as a vector by putting a little arrow on top of it. In books, oftentimes it's written as a bold letter. But so this has a direction. What is the direction? Well, I'll specify it right here. It is an angle theta with respect to the x-axis. So that's one way to specify a vector. But this vector that I've just drawn here, which has this magnitude, the magnitude of this we would write as using absolute value signs. Sometimes people put double absolute value signs, so double bars on each side. I'm not going to do that because it looks messy when you write it on a whiteboard, when I do it anyways. So I'll just write it like an absolute value sign. The magnitude of that, that's the scalar value of it. And we'll talk a little bit more how to get the magnitude of it. But first I want to talk about vectors that are exactly the same as this one. So for example, this vector here, if I specify that it also has the same magnitude as my original vector and the same angle with respect to the x-axis, despite the fact that it's located over here, right, these two vectors would be equal. So you can move vectors around at will. And so that brings up adding of vectors. So how do we add vectors? Well, geometrically, the way that you add vectors is head to tail. So if this is vector, I'll call it vector 1, and I have another vector, let's say vector 2, and I will let it go almost horizontal entirely. I'm free to move this vector up here, like so. So I can completely move that vector over there. And then the way that we add the two vectors is from the tail of the first vector to the head of the second vector. This is the sum of these two vectors, v1 plus v2. What about subtracting two vectors? Well, if we imagine the same scenario here, but instead of adding vector 2, I can add the negative of that. Now, what does the negative of this vector mean? It means that the head reverses direction. It's just going in exactly the opposite direction. So it would have the same angle as the original, but it would be pointed in this direction here. And so now, going from the tail of the first one to the head of the second one, we get that this is V1 minus V2. So that's geometrically, and we're not going to have we're not going to have occasion to use that directly. What we'll do instead is we'll work with vectors in terms of their components. Call this y, we'll call this x. If I have a displacement that takes me 3 units along the x-axis and 4 units along the y-axis, then I find myself with this vector here. Now, what is the magnitude of this vector? The magnitude of this vector, which I'm going to call r since this is a displacement, is equal to 5. Now, how do I know that? Well, because, well, I should make that there. How do I know that? Well, the length along the x-axis is 3, and the length along the y-axis is 4. And by the Pythagorean theorem, 3 squared plus 4 squared equals 5. And so that is the definition of the magnitude of a vector if we write it in component form like this. Before I do that, though, I just want to introduce a little bit of notation that we often use. To write this as a vector, you could do a few things. A lot of people will do brackets like this, where they specify the x and the y components of the vector. That's fine. Some people will do a column vector like this, 3, 4. So that's the x direction, that's the y direction. I think to start, we're going to do it like this. We're going to use what we call the directional unit vectors. So a directional unit vector has a magnitude of 1. It is, in that sense, just a direction. So for the x-axis, we call this the I vector. For the y-axis, we call it the j vector. And if we had a z-axis coming out, we would call that the k vector. And so we would write this vector as r is equal to 3i. And we put a hat on it, and the hat, as opposed to the arrow, means that it's a normalized vector, which means its magnitude is 1. Plus 4j. And if I want to add with, say, a vector of, add an additional vector here, we'll call this R2. And its magnitude is equal to 3. It's entirely in the I direction. So R plus R2 is equal to 3i plus 4j. That's the first vector, R, plus the second vector, which only has an I component, 3i. And so that is equal to 6i plus 4j. So, if we wanted to get the angle that this makes in this 3, 4, 5 triangle, we could use either the tangent function or we could use a sine or a cosine function. And so we know that the sine of theta, this angle here, is equal to the opposite, which would be 4 units, over the hypotenuse, which is 5 units. So what you would do is your calculator has an inverse sine function. It looks like this. It'll say sine minus 1 of theta. You want to make sure that you're set up in degree modes if you want your answer in degree, but that'll be something you can figure out from the instruction manual on your calculator. But you would type 4 divided by 5, and you'd hit the inverse sine button, and it would give you an angle. I can do that if I can find my calculator. It's right here. This should be in degree mode. So I will type inverse sine of 4 divided by 5. Gives me 53.13 degrees. So 53 degrees. We're not going to have a lot of use of things like this. Mostly what we'll be dealing with are problems where the angle is specified and the magnitude is specified. So it would look like this. And we say, okay, we have a vector r whose magnitude is equal to, let's say, 5, and its angle theta is equal to 30 degrees. If I want to know what the x component of this is, right, I can get that because I can just imagine this little right triangle here. We're breaking this displacement vector up into its x and y components. This is the x component, or the adjacent side to that angle. The opposite side to that angle is the y component. And we'll remember that the cosine of 30 degrees and the sine of 30 degrees and the cosine of 30 degrees we had written down easily in the last lecture. But let's just write this here. So r is equal to, and we'll write I for the x component. So that's going to be 5 times the cosine of 30 degrees plus 5 times the sine of 30 degrees. Now, how am I doing that, you might ask? Well, remember, the cosine is the adjacent divided by the hypotenuse. And if I multiply the hypotenuse, which is the magnitude 5, times the cosine, then all I'm left with is the x component. It's just a simple cancellation. Right? So if I take the hypotenuse times the adjacent over the hypotenuse, this cancels and I'm left with just that. So we have 5 times, what is the cosine of 30? Well, remember the mnemonic? For the cosine, it was 3, 2, 1. 30 degrees, so that's going to be the square root of 3 over 2. And that's in the I direction. And for the j direction, it's 5 times the sine of 30 degrees. And so for the sine of 30 degrees, that was the 1. So that's 1/2. So we have 5 halves square root of 3 in the I direction and 5 halves in the j direction. And so these are the components of our vector of magnitude 5 at a 30-degree angle. I think that is all I want to say about vectors at this point. Later, we'll talk a little bit more about vectors. We'll learn how to take special types of products, the dot product specifically, because we'll need that to talk about energy. For now, all you really need to know how to do is to add vectors and break them down into their components. And so we'll see many more examples of that in future lectures.